Exam A, Final Practice Exam A, I'll start kind of working through the back half of it today, and then we'll kind of do the rest of it, or if anyone has specific questions, we can start with those. I'm guessing most people haven't had a chance to kind of go over these, but maybe by the end of the week we'll have some people who have looked over them a little bit and might have some questions. So this is kind of some older stuff. I'll go to the newer information, which starts on question 16, which is referring, looking at two population examples, since we haven't done a bunch of those. I think up here we've got one population example, so we'll start with the two, and then kind of, if we have some extra time today, we'll start working backwards from, working backwards from 16. So question 16 asks for what the 99% confidence interval is for the difference between these two population means, and then we have to assume the degrees of freedom is 50. So I think what I have up here is I sample 40 individuals from Indiana, 50 from Ohio. I find average BMIs in both states, and then the sample variance in BMIs from both those states. Now, we would usually have to use that kind of complicated formula to find the degrees of freedom, so I go to my formula sheet. That equation is on there. Oh, where is it? Right here. But I told you I'm not going to make you use that. I'll always give you kind of this assumed true degrees of freedom, just because it's very easy to make a math error here. So we've got this degrees of freedom 51 and 99% confidence interval. If we look at that formula sheet, we can see that, okay, here's my confidence interval for proportions. Here's my confidence interval when I know the population variances. Here's my confidence interval when I only have sample variances. So I'm going to be using this equation right here. Right. Let me zoom in a little bit on it. So this equation right here. So I'll take the difference that I found in my sample means. I then need to look up a t-value from a student t-distribution that gives me alpha over 2 on each side of my interval, and at my degrees of freedom, which for this one was 50. I was told my two sample variances, my two sample sizes, so it's really just a matter of plugging everything in here, except I have to look up that t-value. So if we go here, look, I've got my sample variances, plug those in, sample means, plug those in, sample sizes. So then it's just a matter of finding what the 99% t-value would be at degrees of freedom 50. So if I have a 99% confidence interval, what area is outside my interval? 1%, which is an alpha of 0.01, right? So if I have an alpha of 0.01, that means I have half of it on each side of my confidence interval. You guys don't want to look at this as supply and demand graphs. So if I've got this interval, I've got alpha over 2 on each side. At the 99% level, my alpha is 0.01. So I have 0.01 over 2 on each side, or 0.005. Right? So I want to find 0.005 as the area of my tail. I go to my student t table. Oh, if I switch off the webcam. So 0.005 in my tail, and at my degrees of freedom of 50, so I gotta keep scrolling down here. Right here, 2.678, right? So now I've got everything I need to plug into this formula, right? I've got 2.678 goes right here. I had 27, 29, I forget what the variances were, 40 and 50 were the sample sizes. Right, it's a matter of plugging things in at that point. Okay. Now, if I look at the difference between these two groups, there's a -2. So my confidence interval should be centered around whatever sample difference I find. Right? If I'm thinking about writing this out, I've got 27 minus 29. I'm going to build my confidence interval around that, plus or minus that 2.678, and then times the square root of, trying to look at it here, so 25 over 40 plus 36 over 50, right? And I'd add that margin of error to my upper bound, subtract that margin of error to my lower bound, but it should be centered around -2. Okay? So when I go back to my formula sheet, -2 better be in smack dab in the middle of my confidence interval. So if I look at these options, -2, right? It's kind of looks like it's okay. It's in the middle of these two. It's not in the middle of this one, right? negative 2 is actually closer to negative 1.2 than it is to negative 4.2. So I can rule that out, and then it's definitely not in my interval D. So I really have a 50-50 shot here if I'm guessing, even if I don't do the math, right? So I think if we end up kind of have the answer keys, as we're working through these, I can kind of mention what the answer is. Oh, it looks like it ends up being A if we do the actual computation. Okay? All right, so 17, we're kind of dealing with the same information, but let's say you want a test statistic for whether or not to test for whether or not Indiana has a lower BMI than Ohio. So in this one, I don't ask you for the null alternative hypothesis, I give it to you. But this is another good one where if you're reading through and working through this exam, remember, well, I want to determine whether or not Indiana has a lower BMI than Ohio, which if Indiana is group 1, that means Indiana minus Ohio. If Indiana's was lower, it would have to be less than 0. Right? So even though I give you the hypothesis test here, you should be able to come up with it. So because you want to know is Indiana less than Ohio, then that difference between the two would be negative, right? Less than 0. So that's what we want to test for. That's our alternative hypothesis. We assume the opposite is true to stack the deck against ourselves, which is that it's greater than or equal to 0. So we look at our formula sheet. We're still dealing with we only have sample variances. Here's my test statistic equation, right? So for each one of these 3 types of examples, we have the means and we have population variances. Here's my confidence interval, here's my test statistic. We're dealing with proportions. Here's my confidence interval, here's my test statistic. Sample means with only sample variance. Here's my confidence interval, here's my test statistic. Okay? So here's my test statistic. It's really just, these test statistics should be easy points. As long as you're identifying it's a sample mean, difference in sample mean problem or a difference in sample proportions correctly, it's just a matter of plugging in your 2 sample means, 27, 29, your 2 sample variances, I think it was 36 and 25, and then your 2 sample sizes, 40 and 50. It's really just a matter of kind of identifying the correct equation. There should be some easier points in the exam. Right? So if you do that, you know it's going to be negative. So right away, right, because the difference that you found, 27 minus 29 is negative, so your test statistic tells you how many standard deviations below the assumed true value that your sample was. When we're looking for differences in sample means, it's telling you the difference you found in your sample means is whatever the test statistic is, number of standard deviations below the assumed true value of 0, right? 0 is kind of always going to be the value in that null alternative hypothesis for us. So we know it's negative, but we plug everything in. We should get negative 1.7, right? So that, once again, test statistic 1 should be pretty easy. So we've got this test statistic. Assuming the degrees of freedom is 50, if we're looking at the 95% confidence interval, what would the critical value be? And what's the outcome of the hypothesis test if the test statistic we found instead was negative 1.55? So I'm giving everyone an assumed true statistic, so we're all starting off on the same foot, so we don't have like cascading errors. We look up here, it's a left-tailed test because there's a less than sign in the alternative hypothesis. So right away we should know that the critical values are negative, right? Left-tailed, left side. Well, if we go to the left side of the distribution, the mean is 0, so anything to the left should be negative. On top of that, we're looking at sample mean, a difference between sample means where we only have sample variances. So we know we need to be using the student t distribution. A good indicator of that is I told you degrees of freedom. So the degrees of freedom of 50, I've got a 95% confidence interval. It's a left-tailed test. So visually what I'm thinking about is I'm trying to find this critical value or the value that gives me my desired alpha in my tail or tails. But here I've only got one tail. It's a left-tailed test, a one-tailed test. So I've got something that looks like this. And I said it was the 95% level. So that means that 5% is kind of outside that confidence or an alpha of 0.05. So I want to find the value, and I know this will be negative, that gives me 0.05 in that lower left tail, and it's a student t distribution with degrees of freedom 50. Right? So I go to my student t table. I say, all right, I want 0.05 in my tail. So degrees of freedom is 50, 1.676. Right? So 1.676, but I have to remember, the student t-table always shows me just the positive values, right? I could come up with the exact same table and make all these negative because it's a symmetric distribution. So if kind of 1.676 would give me 0.05 in the upper tail, negative 1.676 would give me 0.05 in that lower tail. So that's my critical value. Now as far as the rejection decision, if I've got my critical value, all I do is plot my test statistic. So where would the test statistic fall? Well, it's negative 1.55, which is not to the left, or right, not in that rejection region at the 95% level. So because it's not in the rejection region, I'd fail to reject the null. Okay? So negative 1.676, and I'd fail to reject. Oh, the doggos. I see someone out there who doesn't like. So should be A there, right? We did fail to reject, and the answer is negative 1.676. Okay. So let's instead say we have an example where we've got 500 men, 500 women. 30% of men own guns, 31% of the women did, and we want to start to make statements about whether or not there's a difference in gun ownership between men and women. Well, first we'll look at a 90% confidence interval, right? So if I want a 90% confidence interval for this, I go to my formula sheet. I'm looking at the difference in sample proportions. So here's my confidence interval, here's my test statistic, okay? Excuse me. Excuse me. Ooh. So really, it's just a matter of plugging in what we know. We know this for men was 0.37, for women 0.31 was the sample proportion. Plug those in again. Both the sample sizes are 500. All I have to do is look up that z-score. So it's the z-score that gives me alpha over 2 on either side. So when I look at this problem, 90% confidence interval means there's 10% not in the interval, or an alpha of 0.1. However, that's the total area outside the interval. On each side, since I have two sides, it would be 0.1 over 2. I'm looking at a proportion example. So anytime we have proportions, we always should be thinking standard normal or z-table. Okay? So I've got 0.1 over 2, or 0.05 in the tail. So I want to find what z-value gives me that 0.05. So I know the probability, so I'm looking for 0.05. What's as close as I can get? Looks like it's in between these two. So negative 1.64 and 1.65. So I can use kind of the higher of the two, so negative 1.65. However, right, when I'm thinking about doing confidence intervals, that positive and negative are already built in, right? I want to go negative 1.65 standard deviations below to get the lower bound, but then 1.65 standard deviations above to get the upper bound. So I can get the value that way, and just remember, yeah, I'm not plugging negative 61 point, I'm just plugging that value, right? The absolute value, so 1.65. And then it's just a matter of plugging those values in and kind of plugging away, right? Now, once again, if we think about this one, what's the sample difference I found? 0.37 minus 0.31, so 0.06. So my confidence interval should be based around that difference, right? If I look at that formula sheet, I'm adding and subtracting the same value to whatever that difference is I found. So my difference should be, or my confidence interval should be centered around that difference. Okay? So if you look at all these, 0.06, looks like it's in the middle of all these, so I might not be able to rule out any here. So unfortunate, but 0.06, yeah, I can't rule anything out. Oh well. So it's just a matter of kind of having to go through the computation, plugging all those things in. Once you have the z-value, it's really the only kind of tricky part of it. So we should end up getting 0.011 to 0.109. I kind of already got a sneak peek of the test statistic. Once again, test statistic problems should just be a matter of kind of identifying the correct formula. I've got two sample proportions I'm looking for the difference in. I need to use this equation here. Now, this one's a little tricky because we do it in two steps. This kind of, if we have differences in sample sizes, it's not as clear cut as you might think it is. And so here I have an example where we have the same sample sizes, which, okay, this formula will still give us the correct test statistic, but it also works when we have unequal sample size here too. So I'll plug in 500. So first of all, I'll need to do is, if I plug 500 in here, 0.31 here, 0.37. I need to calculate this intermediate value p bar. How do I do that? I plug in the sample portions, the sample sizes, and then once I have p bar, I'll plug that into my denominator. So it's kind of a two-step just to make it a little bit easier. You could do all right. I could write all this out twice in here, and it'd be kind of a crazy-looking equation. What's probably easier is to do it in the intermediate steps. Now, once again, this denominator still represents the standard deviation of something. Here is the standard deviation of the statistic we're looking at, which is the difference in sample proportions. But it's still a standard deviation, so that denominator will always be positive. So in your test statistics, the numerator always tells you the value of the test statistic. Here, the difference tells us what the size will be. If I find, right, because what we're doing is we're assuming that that difference is 0. And so if I find a difference for my samples that is negative, right, then I'm going to have a test statistic, or I'm going to be a certain number of standard deviations below that mean of 0, right, that assumed true mean difference of 0. If I find something that's positive, then I'll be above it, right? So here I found something positive, 0.37 minus 0.31 is 0.06, so I should have a positive test statistic, so it should be B, C, or D. Right? And from there, it's just a matter of entering things in that equation. We end up getting D here. Right? Now, once again, to start us all off on the same foot, in 21, I give you all an assumed true test statistic. So 1.45, so assume that's the test statistic that we found in 20. What would the p-value be? And I said, what's the outcome of the hypothesis test? I cut that off here, but we can kind of talk through that as well. So I give you the hypothesis test here, which is that we're assuming the difference is 0. We're looking at if an alpha is 0.05, then we're looking at the 95% confidence level. So we want to find the p-value given this test statistic and then determine whether or not we can reject. So it's a two-tailed test. So what we're going to do is we have a two-tailed test. So now, instead of finding the critical value and using the critical value approach, what we're going to do is we've got this test statistic of 1.45. So we can find the probability that we saw that test statistic or something more extreme. If it was a one-tailed test, this would be our p-value. But we have two tails, so it would have been equally as likely we saw something 1.45 standard deviations below the mean. So whatever we find here, we're going to have to multiply by 2. Right? So I can look up 1.45 on my table. We're going to look it up on the z table now, because we're looking at proportions. So I have that z value, that test statistic of 1.45. So we go down here, 1.45, so 0.9265. So 0.9265 is the area to the left of 1.45. I want the area to the right, so I have to subtract it from 1. So what, 0.0735? However, that's only one of my tails, so I still have to take that, and to get my total p-value, multiply it by 2, or 0.1470 is the p-value. So the rejection decision was kind of left off that, but this should be our p-value. Do we reject or fail to reject at the 95% level? Well, we only reject if that p-value is less than alpha. Our alpha was 0.05. Our p-value is 0.1470. It's not less than that, so we would fail to reject, or we do not reject. Okay? All right. Try to get this whiteboard not to fall. Okay, so that should give us our answer, 0.1470, and then if we wanted that outcome, we would say that we failed to reject. Okay. And kind of the key here is when you see a not equal to sign in the alternative hypothesis, you know it's a two-tailed test. So we know we have to multiply that p-value by 2. You can't just stop when you find the area in the tail for a two-tailed test. You have to multiply by 2. But it's only for a two-tailed test. Moving on to 22. So let's say we have this example where we're looking at calorie consumption before and after they post calories on the menu at McDonald's, right? We got 42 individuals. We find a mean difference of 50, negative 50, and then a variance of these 42 individuals of 2,200, 500. 2,200 now. 22,500. So if you want to do the test that has calorie consumption decreased, right, is that average difference negative or less than 0? We're told the alpha is 0.05, so this is a 95% confidence interval, or confidence level. Calculate our test statistic. Well, go to the formula sheet. Our matched pairs stuff, or looking at this mean difference, is down here. The test statistic's really easy. It goes back to where it's almost like a one population example. So all we do is take that average difference we found, divide it by the square root of that variance we found in the difference, divided by my sample size. Okay? So if we go back to our problem, we have the mean difference was negative 50, the variance was 22,500, and my sample size was 42. So really, what I'm thinking about is, if I was doing this on the exam, what I would do is, I looked up the formula on the formula sheet, right? This is what it told me. Right. The problem gave me those values, negative 50 over square root 22,500 divided by 42. Right. Write out the formula that you get from the formula sheet, plug the values in so you have the exact same format but with the numbers. Right. Now you're done. If you do this, I think you get negative 2.16. Let's double check here. Yeah, plug those in, we should get negative 2.16. Okay. So once we have our test statistic, let's assume that instead we found it was negative 2.5. What's the critical value of this test? Well, what do we need to know? Well, to find a critical value, we need to know the type of test and what our alpha is. Well, our alpha is told to be 0.05. We have what type of tailed test? Well, in the alternative hypothesis, there's a less than sign. So less than sign, left-tailed test. So what we want, right, is what's the value that gives us, in this left tail, an area of 0.05. Now, we did this one earlier, but we did it for proportions. Now we're dealing with a sample mean. And so, sorry, not sample mean, a mean difference. And so we're trying to find this value that gives us a area of 0.05, but this is a student t-distribution. Right? So I know the area I want in the tail. I need to find my critical value. So I go to my student t-table. Degrees of freedom is what? Oh, well, I get a sample size of 42. So this goes back to now, when I want to find my degrees of freedom, I'm not going to give you the assumed true value because it goes back to simply being the sample size minus 1. Right? So it's a sample size minus 1. So 42 is my sample size, so my degrees of freedom should be 41. I wanted 0.05 in that lower left tail, so 1.683. But remember, it's a left tail test, so it's 1.683. But if it's on the left side, it has to be negative. So negative 1.683. What's my rejection decision? Well, I was told to assume that the test statistic was negative 2.5, so where would that fall? Well, if I plotted it, right, somewhere out here. So it's definitely in my rejection region. So here's my critical value, and my decision should be that I reject. So if we go to the answer keys, we should find, oh, there might be a typo here. Let's see. I bet it's right in the answer key and I copy and pasted it over. Yep, okay. So it should be C, but somehow when I was doing this, I accidentally deleted the negative sign. So I'll repost this practice exam with this change. Let me save this and I'll post this. So negative 1.63 we should reject. All right. So those were a couple examples of some of the new two population stuff that we've been doing. The next stuff we're going to go over is some of the linear regression. Okay. So this is some of the newer stuff. Let's say I've got this table below and I show you the output from a multiple regression where the dependent variable is wage, which is measured in dollars per hour, and the independent variables I'm using are age, experience, education, all measured in years, and then gender, which is a 1 if they're male and a 0 if they're female, right? So I've got 50 observations. I run this regression. I get an R squared of about 0.37. So I'm explaining about 37% of the variation in wages with just these 4 variables, right? Which kind of makes sense. Education, experience should kind of be pretty good predictors. I give you the rest of the output. I don't give you the test statistics, right? So if we go down to one like 25, what's the test statistic for the age coefficient? Well, if we looked at what I did yesterday with this regression output, I actually said in Excel it's pretty easy. I add another column, and all I have to do is take that coefficient and divide it by the standard error, right? So for age, negative 0.019 divided by 0.083 should be what? Right around negative 0.229, right? If I just divide that coefficient by the standard error. And I actually hid these so you can actually see all the test statistics here. But each one you should be able to come up with. For education, take the coefficient of 1.23 divided by 0.367 should give you the test statistic of 3.35, right? So you could find all of those kind of using here. Yeah, just coefficient divided by standard error. So for 24, what's the correct interpretation for the coefficient on education? So the interpretation for any one of these variables is a 1 unit increase in the x variable would cause whatever the coefficient is, prediction of the y variable to go up or down by that amount. So for education, for every 1 additional unit, 1 additional year of education, we would predict that hourly wages go up by $1.23. Okay. If I wanted to interpret age, for every year a person gets older, their predicted hourly wage goes down by what, $0.01 or $0.019 or about 2 cents, right? Holding everything else constant. So the reason why this, you might think, oh, people get older, they make less money. Well, think about, if we're not just looking at age, we're saying hold constant the education of an individual, hold constant their experience, like the same years of experience, same years of education, they're both the same gender, but one of them is 1 year older, we would predict their wages a little bit lower, right? 2 cents lower. Now, if we look at the p-values, even though that is the interpretation, is that statistically significant? Can I say that there is that effect from age on hourly salary with a high level of confidence? Well, this p-value is 0.8, right? We always start out assuming what? With these linear regression examples, we always start out assuming that every single coefficient, right, the null hypothesis is always that these coefficients are equal to 0. So if I have a p-value of 0.8, that's definitely not going to be less than any alpha that I'm looking at. So I fail to reject, I'm failing to reject this. I didn't find enough evidence that goes against there being no relationship. So when I'm looking at the p-value on age here, 0.82, okay, I interpreted it correctly, but really that's not a reliable interpretation because it's not significant at any level, right? I can't say that effect exists with 90, 95, or 99% confidence. Hell, I can't even say it with like 30% confidence, right? Because 30% confidence would be an alpha of 0.7, and my p-value is still not less than that. So really, it doesn't look like there's a strong relationship between age and hourly wages once we account for the education and experience level of the individual. Okay. So that's kind of just a little quick, linear regression. I added some stuff in there about looking at p-values. Like I could ask you a question like, which of the following variables in the variables that were included in the regression have a statistically significant effect at a 95% confidence level on wages. So your alpha would be 0.05 at 95% level. So you go through, well, the intercept is significant because it's less than 0.05. Education would be, experience, but age and gender wouldn't be, right? Because they're not less than 0.05. So the only ones in which we could reject the null or say they had a significant effect at the 95% level would be education and experience, and if you wanted to say the intercept as well. Another one we could do is, what's the interpretation of the gender variable here? So remember, gender was a 1 if male, 0 if female, or 0 if not, I guess. And so it's a 1 unit increase in my x variable. If my x variable is a 0, 1, then 1 unit increase would be going from a 0 to 1. So I would say a male relative to a female, right? The 1 category relative to the 0 category, however that's coded. If this is a 1, going from female to male, the wages we would predict would be about $2.29 higher, even if we held everything else constant. So 2 people with the same education, same experience, same age, but one of them is male, looks like there's a slight kind of premium on that, right? Now, we can't say that that's statistically significant, right? P-value is pretty high, 0.18, but that's how we would interpret the coefficient. Okay. Throat's getting a little coarse here. Okay, let's go back. I kind of want to do a little bit more. I'll save some of that for later in the week. I'll go back to some of the early stuff. We'll start working through it just to kind of show you, hopefully, that it's kind of helpful to have them. So let's go all the way back to some of the stuff that we went over at the very beginning of this class, right? So let's say I start out the exam, I give you something like this, where I get 5 states and their unemployment rates, right? Find the sample mean of this small data set. Well, all I have to do to find a mean should be really easy, right? Add up the numbers and divide by the number of numbers we have, right? That was kind of where we started this class. It should be a really easy one. If I go back to my very first formula sheet, right? The mean is you add up all the values and divide by the number of values you have. So here, 5.9 plus 5.2 plus 5 plus 5 plus 4.5, divide that by 5. Now, what has to be true is, if I'm looking for the mean has to be somewhere in the range of these values. So it has to be somewhere between 5.9 and 4.5. So if I even just look at these, only A and C even fit that criteria, right? And I think if I actually work this out, the answer ends up being C, okay? But B and D, those are larger than even the largest observation I have, so there's no way that could have been my mean. What about finding the sample standard deviation? Well, honestly, this is where I said, I'll type this out as I'm saying it. What I want to do is find the difference between the value and the mean, or the deviation from the mean. I want to square it. I then want to add them all up and divide by n if it's a population data set, and n minus 1 if it's sample data set. So I'm doing this off my top of my head, but remember, here's my population variance, so I add up the deviation from the mean squared for every observation and divide by n if it's a population variance. If it's a sample variance, it's the same procedure, but I divide by n minus 1. So here we were asked for the sample standard deviation, so we divided by n minus 1 or dividing by 4, right? 5 minus 1 is 4. So I'd go through 5.9 minus 5.12, and maybe on the exam here I give you an assumed true mean, so just in case you got one wrong, you didn't get this one wrong, I then go through 5.2 minus 5.12 and then squared. Oops. I would then kind of do this for each one of these. I would then add them all up and then divide by n minus 1, so divide by 4. Right? Now, at that point, I should have, so let me see if I go through, I'll kind of do this and then we'll talk about, so I can give you the actual numbers, the intermediate numbers. So 5.2 minus 5.12 squared plus 5 minus 5.12 squared plus 5 minus 5.12 squared and plus 4.5 minus 5.12 squared. So 1.028 divided by 4. 0.257 should be what I get, but that's my variance. To get the standard deviation, I would have to take the square root of 0.257, which ends up being approximately 0.507. Okay? So if I add these all up and divide by n minus 1, which is 4, then what I should get is that 0.257, but that's my variance. So to get the standard deviation, I'd have to take the square root of that. Okay? All right. this. So we then have kind of these probability questions that you might want to kind of review a little bit. That shouldn't be too bad once we start looking at them. So let's say the screenings for HIV are very reliable but not perfect. Probably an HIV test shows up positive, given the individual has HIV, is 0.95. However, the probability the test shows positive given the individual doesn't have it is 0.01. Recent estimates show about 2.5% of people have HIV. Okay? So we can run with this example. First thing we want to do is just kind of write down what we were given. Right? So if I write down what I was given here, the first thing I was told was, and hopefully if you're watching this, you can also pull this up, so when I switch to the webcam, you can see what I'm referencing. So the first thing I was told was the probability the test shows positive, so the probability the test shows positive, given that the individual actually is HIV positive. And if it helps here, you could write the probability that test shows positive, given the person is HIV positive. I'll actually write it out like that. So that was what, 0.95? And the probability the test shows a positive, given that they actually are HIV negative, well, it was 0.01. There was 1% false positives. We're then told the probability, without any additional information, that someone is HIV positive is 2.5% of the population, or probably 0.025. So this is what we were given. Using this information, we want to find, in problem 3, what's the probability that if a test comes, that individual has HIV and the test comes back positive. So what's the probability that somebody is HIV positive and the test comes back positive? Right? So we have an intersection of two events. What we can do, if we go to the formula sheet, the intersection of two events is a conditional probability times what we're conditioning on. Right? So conditional probability times what we're conditioning on. Remember, what we condition on is what's on the right-hand side. That's our given. So we want to find this intersection. So I know I can rewrite this as, oops, I want to go to the webcam. So I know that I can rewrite this as, I'm kind of running out of room here. So the probability, this one's HIV positive, and the test comes back positive, is the probability of the test coming back positive given a person has HIV. So this is a positive up here, divided by whatever I'm conditioning on, which is the probability that someone is HIV positive. Right? So all I did there was I took my formula sheet. I knew that I was working with this equation, sorry, this one up here, and actually I wrote that down wrong, didn't I? It's not divided by, I just ran out of room. It's multiplied by. So this would be that conditional probability times the probability of what I'm conditioning on. There we go. Right. So I just plugged in my A's and B's. Now this one's a little tricky because of the way I kind of the direction of the words. Remember, the intersection could be equal to this, or it could be equal to this, because the order doesn't matter. A and B is the same thing as saying B and A. Right? So either one of these I could check to make sure if they work. In this one, it kind of was nice because if I wrote this out the way that it was worded, everything worked out, and then this one was the very first one I could use. But if I would have instead stated the question as, what's the probability someone gets a positive test result and has HIV, well then if I wrote it out kind of in this format, it would be something I don't have, but if I wrote it out like this, I would see that I have these probabilities. So you might have to try both of these equations when you're solving this one. Okay? So if we end up plugging those values in, right, at that point, it's just a matter of what's the probability someone has HIV? Well, I have this down here being 0.025. What's the probability that, given that the test comes back positive, they test positive? That's 0.95. So 0.95 times 0.025 which if we look here, I believe should give you 0.02375. Let's check on the answer key just to make sure. Yeah, 0.02375. Okay. Now, at this point, probably one of the harder questions on the exam, specifically one of the harder review questions on the exam, is going to be one like 4, which I'll tell you right off the bat, we're going to have to use kind of Bayes' theorem for that. And so this is, we're told, given the test comes back positive, what's the probability the person actually has HIV? Okay. So given that the test comes back positive, what's the probability they actually have HIV? So this is where not having the board space kind of sucks, because I don't want to really get rid of all this, but hopefully you can kind of go back. I need to have a little more board space and remember what those probabilities that we were given were. You have them written down. Right? So now we want the probability that, given that the test comes back positive, wait, I said that backwards. What is it? Yeah, okay, sorry. Well, given that the test comes back positive, what's the probability the person actually has HIV? Well, if we go to our formula sheet for the first exam, we try to say, okay, I've got a conditional. Okay, I can write it out this way. Right? So it's just the intersection of the two divided by what I'm conditioning on. So if I look what I'm looking for, this is my A, this is my B. I can rewrite this as the probability of A and B, and excuse me, divide by the probability of B, what I'm conditioning on. But the problem is, if I look back at what I was given, I don't have either of these pieces of information. So if I'm looking for a conditional probability, and I write that out and I can't do it, it's probably a pretty good indicator I need to use Bayes' theorem here. So now I've got a conditional probability I can rewrite like this. So what I would do if I'm doing this on the exam, write down the probability of what you're looking for. Right? This is your S, this is your E. Right? I would then go through and walk through this formula and write it out in the context of your example. So the probability of S times the probability of E given S. So the probability of S times the probability of E given S. Right? Divided by, we go back to our formula, the same thing in our numerator, so we could just rewrite all that out again, plus the probability of S complement times the probability of E given S complement. So let's write that out. So the very first part is just the probability of being HIV positive times the probability the test comes back positive, given that they are positive, they have HIV, plus the probability of S complement. Well, if this is S complement would be being HIV negative, right? If S is being HIV positive, S complement is being HIV negative, and then this gets multiplied by, I'm going to run out of room here, so I'm going to write it here, the probability of E, so that the test comes back positive, given S complement, which is that they're HIV negative. From here, we were given all this information at the get-go. Probably someone is HIV positive is 0.025. Given that they have HIV, the probability that the test comes back positive is at 0.95. The probability that the test came out positive given they didn't have it was 0.01. And the only thing we weren't directly given was, but we can figure out pretty easily, is what's the probability that someone's HIV negative? Well, if the probability that someone's HIV positive is 0.025, the probability they're HIV negative would be 1 minus that. Those two events are complements, right? They have to add up to 1. So now we've got everything we need. Now it's just a matter of plugging that into our calculator. All right? I'll kind of show you a close view of this. You can pause it here in the video if you need to. Okay? All right. So if we do all of that, I think it's 70.9. Yeah, 70.9%. So, I'm trying to think which ones I want to work through today. We'll go back and look at these. So, some other ones I could ask you from that first exam would be, I think it's from that first exam. Let me double check. Excuse me. Yeah, so these binomial guys. So I might ask you a couple binomial questions. So this is kind of an important concept to leave the class knowing. But let's say I've got 35% of Americans have a college degree, and I choose 10 people at random. Right? So I use this example a lot in class, so this should be hopefully an easy one to kind of remind us what a binomial distribution looks like. So what would the variance be? If we look at this formula sheet, all of our binomial equations are down here. So you have the added benefit. I am not locking you out. So on your formula sheets, you could write down what all these are. So it might be good to write down, these are my binomial equations. Right? So here's my variance equation, n times p times 1 minus p. My n is the number of trials, or 10 people I'm looking at, so 10. The probability of success for any one person is 0.35. So 10 times 0.35 times 1 minus 0.35, that would give me the variance, which I think is probably 2.275. I'm thinking about this correct off the top of my head. Yeah, 2.275. I could ask you for the standard deviation, which only additional step you would have to do there is what? Take the square root. Okay. If I then ask you, and what's the mean? The mean was really easy. Remember, we said if probably any one person has a degree is 0.35, and we've got 10 people. Well, what's the expected value, or what's the mean? Well, it would just be 10 times 0.35, right? N times p. And you have the formula for that as well, but that one was one we said is pretty intuitive, right? The mean is pretty intuitive for a binomial. If and with the probability exactly 4 people have a degree, now we get this added component, which is x is equal to 4, right? Now, first of all, we're looking for a probability, so it should be somewhere between 0 and 1. But if you think about what's the most likely outcome here, well, if on average we see 3.5 people out of 10 have a degree, then seeing exactly 4 is probably fairly common, right? So A doesn't make a lot of sense here. It's probably going to be one of these three, right? So I've got my x is 4. I've got the probability I see x being any one value here. I've got n is 10. My probability of success on any one trial is 0.35. My x is now 4. It's a matter of plugging and chugging, right? Kind of, hopefully, what I would do is go back, hopefully remember, but find that factorial button on your calculator. If you need any help kind of prior to next week finding that, we can WebEx or something that can try to help you make sure you can identify that. But remember, the factorial was like, if it's 4 factorial, it's 4 times 3 times 2 times 1. Right? But yeah, it's just a matter of plugging those values in there. Okay? So if we do that, I'm guessing it's probably B, yeah, 0.2377. And that's just because, remember, the probabilities have to add up to 1. So the probability that I see 0 people have a degree, probability of 1, exactly 2, all the way up to 10, those have to add up to 1. So even the most likely outcomes of 3 and 4, right, they can't be too much, like too large a piece of the pie. They'll be the largest piece, but if it was, say, 0.62, well, that doesn't leave much of a probability for seeing exactly 3 or exactly 2. And even if the average is 3.5, it's pretty likely we'll see 2, 3, 4, 5, in any random group of 10 people. So what's the probability 2 or more people have a college degree? Well, in this one, if I want the probability of 2 or more, what I'm really saying is, what's the probability that this variable x is greater than or equal to 2? Well, what this means is this is the probability x is equal to 2 plus the probability x is equal to 3 all the way up to the probability x is equal to 10. Well, each one of these, to find x being exactly one number, I have to use that equation. So I have to use it what? 8 times here? Right? And actually, no, 9 times. So 2, 3, 4, yeah. So I don't want to do that. Right? That seems like way too much work. And so instead of doing that, what's another way I could find this? Well, if this event was A, then I know this would be equal to 1 minus A complement. So what's the complement of this event? Well, x greater than or equal to 2, the complement of that is x being less than 2. What are the only things that fit this criteria? Well, if it has to be less than 2, then it could be 1, or it could be 0. Remember, this is binomial. These are discrete. We can only see, we can't see half a person have a degree. And so now I only have to use that binomial equation twice, once where x is 1, once where x is 0. Once I find both those, add them up and subtract them from 1. Now, just off the bat, if I know the most likely outcomes, right? So the mean was 3.5, so the most likely outcomes were 3 and 4. 1 and 0, as I move further away from that expected value, those outcomes become less likely. So these should be relatively low probabilities, and then when I subtract them from 1, I would guess this is going to be something that's relatively high, right? Because these are going to be relatively low, subtract them from 1. I should get something probably around 0.8, 0.9. Now, I don't know exactly what it is. So in fact, when I look at the answers, okay, I don't know exactly. Probably either C or D. It's kind of hard to really envision, without doing the actual math, which one of those it's going to be. But I know that it's definitely not going to be 0.08, right? I know it's not going to be something that low. So sure enough, if I plug those values in and I add them up for the probability x is equal to 1 and 0, when I subtract it from 1, I get about 0.91. Right? Okay? So it's kind of a review of the binomial. And you know what? We could almost work through all of these today, so I think I'm going to try to do that. Right? Just make one longer kind of video here. So let's say I have this random variable x, and it denotes the weight of a male deer in Indiana. Right? So I know the variance and I know the mean. What's the probability that a single male deer chosen at random is greater than 165 pounds? Okay. Oh. So, got the information given to me. Like I said, hopefully you have the Word document pulled up while you're watching this, because I can't really have both of them shown to you, unfortunately. I can hop back and forth between them. So what I was told was, I've got this variable x, which is the weight of a male deer. On average, they're 170 pounds. And the variance is 25. Right? So I want to know what's the probability if I chose, select a single deer, that it's greater than 165 pounds. Well, right away, I should know that the area to the right and left of the mean is 0.5, so this probably has to be greater than 0.5. Right? If I actually look at the answer key, we'll go back. There's only two values greater than 0.5, so right away I can rule out all but two of the answers. Now, how do I actually solve what this is? Well, I need to turn this into a z-score and then find the area to the right of it. Right? Well, if I don't remember how to do a z-score, I can go to my formula sheet for that second exam, and it reminds me, when you want to find the z-score for just any variable, we'll zoom in here, you take the value you're interested in, you subtract the mean, you divide by the standard deviation. Right? So for us, that means we're interested in 165, subtract the mean, divide by the standard deviation. Well, here's the variance. The standard deviation would be the square root of that. Or the square root of 25 is 5. So this one's actually pretty easy. How far away is the x value from the mean? Well, it's 5. 5 away. What's our standard deviation? 5. Remember, the interpretation of the z-score is the number of standard deviations below the mean. So the z-score here would be -1. If I then go to my table, and here we're not dealing with samples, we're dealing with the original variable, and we convert them into z-score. So 1.0 is my z-score, so 0.841, sorry, it was -1, not +1. So -1.00. So 0.1587. So if I'm drawing this out visually, this area over here is 0.1587. But that's not what I wanted. I wanted the area to the right. So to find that, I need to do 1 minus that. So 1 minus 0.1587, which is about what? 0.834, or what is that? 0.8413, sorry. So we go back, we'll look at the answer key, 0.843. And remember, if I would have just started out initially where I said, well, look, I'm looking at a value that's to the left of the mean, so when I look at the area to the right of it, I know it had to be greater than 0.5. I could have prevented myself from forgetting to subtract it from 1, because I said, look, I know it has to be greater than 0.5, so automatically I'm going to cross off C and D. Right? And we do the work, we end up finding it's A. Right? So what if I wanted the probability that I choose a single deer that's more than 160 but less than 180 pounds? Right? Well, it's going to be a kind of a similar setup. Right? I've got all the same values in terms of the mean and the standard deviation. But now, I want to know what's the probability. It's what, 160 and 180 did I say? Yeah. 160 and 80. So I want the area in between here. So what I need to now do is convert these into z-scores. Now, I chose these numbers because notice, they're both the same distance away from the mean. So they should have the same z-score, but one will be positive, one will be negative. So if I turn this into a z-score, 180, I subtract the mean of 170, I divide it by that standard deviation, which the variance was 25, so we said the standard deviation is 5. So we get 2, and it's the same distance away from the mean, so it'll be negative 2 standard deviations below. Right? So now what I want to do is, I want to find the area to the left of negative 2, and I can subtract that from the area to the left of positive 2. So I look those values up in my z-table. The area to the left of negative 2, 0.0228, and the area to the left of positive 2, 0.9772. All right? So 0.0228, 0.9772, subtract the smaller one from the larger one, and I'm left with the area that's in between, which is about what? 0.95, no, 0.954 something? Hold on. Let's see. Oh no, 0.9544. Yeah, there you go. Oh, I wasn't showing you the screen. 0.9544. Right. So that's how we find the probability being in between two values. Right. All right. Now suppose we're running with the same example, but we select 10 random deer. Right. So now we're looking at sample means. Well, we know that sample means will be normally distributed around whatever the population mean was, but that the variance of our sample means, right, if we look at the formula sheet, you can kind of remind us, the variance of our sample means is take the original variance, divide by the sample size. Okay? So here in this problem, I'm going to have the mean of my sample means will be whatever the mean of the data I'm sampling from was, so 170, but that variance, right, that variance is going to be whatever the original variance was divided by the sample size. So here, the variance of my sample means is the original population variance of 25 divided by 10, or 2.5. But when I'm looking at this distribution of sample means, it's still centered around that population mean of 170. Okay. So the answer there is 170 and 2.5. Using this information, this is the one problem where, I said this on the second exam as well, I can't give you an assumed true value here. You're going to have to really make sure you know how to correctly identify the mean of sample means and the variance of sample means, because then at 11 you'll have to use it, right? So what's the probability that the sample mean weight is greater than 168 but less than 172 from these 10 randomly selected deers? I shouldn't say deers, it's deer, right? So from these randomly selected deer. So if we go back, what I'm really thinking about is, okay, what's the probability that the mean weight is between 168 and 172? Well, I want to turn these into z-scores. So what I'll do is, the z-score, if I look this up in the formula sheet, I'll show you in just a second, it's going to be, take the sample mean value you're interested in, subtract the mean of your sample means, and divide by the standard deviation of your sample means. However, we do know these values. We actually just found them, right? The mean of my sample means was 170. The variance of my sample means was 2.5, so the standard deviation is the square root of that. But if I plugged in the equations that I have for this, it should be something like this, right? So I could plug all the values in here, or I could remember I already know these two. It makes it easy. So I could take 168 minus that 170, divide by, what, that square root of 2.5. If I do that, let's see. I'll pull this out here real quick. Shut the door real quick. Where did I put my calculator? Here it is. So we get what? 2 divided by the square root of 2.5. About 1.26. Right? So about 1.2, negative 1.26, sorry. And this is the same distance away, so once again, I know it's the same z-score but positive. Right? So I looked up what's the area to the left of negative 1.26. So I go to my table. Z table, I say 1.2, oops, let's see if I can get the columns up here so it's easier for you to see. 1.26, so 0.8962. Well, that's the area to the left of 1.26. If one of the areas to the right, I could subtract that from 1. Or I could look up that negative 1.26. So where's the 0.6 column? Right here. So negative 1.26, 0.1038. So 0.1038. All right. But then the area to the left of this, I looked up, was like what, 0.8962. So subtract the smaller from the larger one, and what I'm left with should be, 0.7924. Right? If I subtract that 0.1038 from the 0.89, is it 42? I should get that 0.7924. Right? So it's the same process as the one we did before. It's just finding the z-scores a little bit more complicated, right, or a little bit more difficult. All right, a couple more we'll kind of work through here. So let's say on number 12, I want to find a confidence interval for the proportion of people who are going to vote for Donald Trump. I take some sample. I find the sample proportion is 0.3, so 30% of people, and then this is of 120 Republicans, and so I've got my sample size as well. Well, here I've got one sample, so this is kind of what we done in exam number 2. I've got my one population examples. Here it's when I have a mean and a known population variance. Here it's a mean and only a sample variance, or I've got a proportion. Well, this is one where we're really given the sign. This is a sample proportion. So once I have that sample proportion of 0.3, I can plug that in here. Sample size is 120. The only hard part here is finding that z-score. So I need to find the z-score that gives me alpha over 2 on either side of the interval. If it's a 95% confidence interval, my alpha would be 0.05. All right. So I've got a confidence interval of 0.05. Sorry, not a confidence interval of 0.05. I have a confidence interval of 95%, which means the area outside of it is 5%, or an alpha of 0.05. But on each side I have alpha over 2, so 0.025. So I want to find the z-score that would give me that area of 0.025 on the left. And the reason why I know it's a z-score is because I'm dealing with a sample proportion. All right, the formula sheet even reminds me, confidence interval for a sample proportion, use that z-score. So I go to my z-tables. I know the area in the tail that I want is 0.05 divided by 2, so 0.025. So I search for 0.025. What's as close as I can get? Oh, it's exactly here, negative 1.96. Now I'm looking at this formula sheet, right? There's already the positive and negative built in, so I just plug in the absolute value of that 1.96. Okay? And that's just a matter of doing a little bit of math. Now, remember, 0.3 has to be smack dab in the middle here. It doesn't look like it's not for any of these, so I don't think you can rule any of these out. And looks like I have a couple typos here for some reason. I accidentally put 2 decimals. I didn't mean to do that, so we'll save that. Okay. So we end up kind of doing the computation. Once I kind of show you how to plug things in, I think you can kind of probably figure out the rest. If you're having problems coming up with this, let me know. But once you have that correct z-value, it should be pretty easy. Okay. Let's say you want to do a hypothesis test of the population proportion of auto workers. Well, I changed the example here. Not auto workers. Let's do people who will vote for Donald Trump. I'm sure I used some copy pasting at one point and changed the example. So let's say you want to test for whether or not the population proportion of people who will vote for Trump is greater than 0.225. What's the value of a test statistic and the p-value? Well, right away, I found a proportion that's greater than this assumed value. So I know that I'm going to be a certain number of standard deviations above that assumed true value, so I'm going to have a positive test statistic. So right away I can rule out A. But really, I know I want to find a test statistic, so I go here in my formula sheet. Here's my test statistics. I'm looking at a proportion example, so I use this one. It's going to be a z-value, so I'm using the standard normal distribution. I found a sample portion of 0.3. The assumed true value is 0.225, so I plug those in. Sample size is 120. These test statistical ones, once you identify the equation, should be relatively straightforward. But notice that denominator, remember, represents standard deviation. So this is the standard deviation of a sample portion. This is the standard deviation of a sample mean with only a sample variance. This is the standard deviation of a sample mean with a population variance. So standard deviations are always positive, so the sign of your numerator tells you the sign of your test statistic. Right? If my sample proportion is above the assumed true value, I'm going to be a certain number of standard deviations above the mean, right? Or above the assumed true mean, so it should be positive. If I'm below that assumed true value, I should have a negative. Well, we found 0.3, the assumed true value is 0.225, so this should be a positive test statistic. But if we actually go through it and calculate it, I think it's 0.1967? Yeah, 0.1967. How do I get the p-value? Well, it's a right-tailed test, right? So when I'm thinking about a right-tailed test and I want to find the p-value, I just found a test statistic of 1.967. I know I'm using a standard or a normal distribution or a z-table, so I can only look this up to the second decimal, so I'll go look up 1.97. So I go to my z-table, I look up 1.97, so 0.9756. So this was 0.9576. Nope, I flipped these. It was 0.9756. Right. I wanted the area to the right, right? For a right-tailed test, my p-value is the area to the right of my test statistic. So I subtract that from 1, you get what, 0.0244? Okay. So that's my p-value. If I had asked for the rejection decision here, right, what would I reject it? Well, if my p-value is 0.02, I only reject if the p-value is less than alpha. So is it less than 0.1? So yes, I can reject at the 10% significance level. Is it less than 0.05? Yes, so I rejected the 5%. Is it less than 0.01? No, so I would fail to reject. So reject, reject, and fail to reject. Okay. Assume the test statistic is 1.5, then we reject the null hypothesis at which of the following levels. Well, if the test statistic was 1.5, right, we could look up the p-value for 1.5 and do the exact same thing, right? Once I have that p-value, just compare it to those alpha values. If it's less than the alpha, I can reject at that level. If it's not, I would fail to reject. I think if I look up 1.5, we could do it. So 1.5, 0.9332, we wanted the area to the right, so 1 minus that, so about 0.06-ish, right? 0.06 would be less than 0.1, so I could reject at the 10% level. It's not less than 0.05, so I failed to reject at the 5%, and it's not less than 0.01, so I'd only reject at the 10% level. Okay. And then finally, which of the following situations could we use a standard normal? So I'll kind of end this answering this question. I won't specifically answer this one, you can look at the answer, but kind of just give you more generally a good way to kind of sort out everything that you're working through. So we've got a lot of types of examples, and knowing whether or not you use the student t distribution or the standard normal, I'm going to set out every single type of example. So we have one populations, we're looking at a sample mean, and we know the population variance. We also have sample proportions. We then have situations where we have two sample means, and we're looking for the difference between them, and we know their population variances. We also have the situation where we're looking at the difference between sample proportions. Right? These are all scenarios where we can use that standard normal or the z-table. If we have an example where we have a sample mean and only a sample variance, or two sample means, and we have the sample variances for each, or we're looking at a mean difference and we only have its sample variance, or finally, we're kind of getting these coefficient estimates from a linear regression, and we have that standard error, right? All of these are scenarios where we can use the student t distribution. All right. So this kind of hopefully can help keep them separate. Anytime we see proportions, z table. Anytime we have known standard deviations, z table. Every other scenario, when we only have sample variances or standard errors, we use the student t. Okay. So that should hopefully, kind of leave this up for a second. You can pause on it. That should hopefully help keep everything kind of sorted for the exam. Okay. All right. So that should kind of cover the exam review for today. We went through all of practice exam A. If you have any questions, please let me know. Like I said, that exam will be posted Monday. You'll have the entire week to complete it. I would expect there might be a small short answer portion at the end where you might have to upload something in similar to the last exam. So be prepared for that. It would be something like the last one where it's like a 2 population hypothesis test question, or maybe something like linear regression where I ask you to write out maybe an interpretation. So not tomorrow, but later this week, I'm thinking Thursday or Friday. I'll let you know exactly when. I'll send out an email or announcement tomorrow. I'm going to try to record another one of these short review sessions where I have some additional practice problems, probably more linear regression stuff. But if you have specific questions, you can, once I announce the date and time, I'll do it live so you can come in and ask those questions. Or if you have questions from exam B, I could go over some of those as well. Other than that, I should cover it for this first exam review. I guess I'll do at least one more during this week. Okay.